Okay, so welcome back to part 2 of this projectile motion problem. So, you know, you recall we're working on this football problem here, and we're actually, this is the part we left off at. So we kind of had our equation to find the time of flight of the football, and we have all our givens, and so essentially our unknown, we're looking for delta t. So we have all this information, so the easiest thing to do is we can easily substitute that in. So sub in, and remember we're solving for delta t here. Now a lot of you might be confused as to why I'm writing delta dy as 0, and I did kind of mention this in part 1, but I'll just go through it again. I'm saying that there's no change in position in the y direction because of the simple assumption that I'm taking that Drew Brees and Marquise Colston, I'm assuming they have the same height. So when Drew Brees launches the football, if Marquise Colston were to catch it, he will catch it at the same point in height. So essentially, from top of Brees' head to top of Colston's head, it's the same height. So therefore, there's no change in position. So yeah, we do throw the ball, it goes up in the air, but it kind of lands back at the same point. So therefore, your delta dy is 0. So this is why I'm taking it as 0, because again, in this problem, this is kind of like a medium complexity projectile motion problem, I guess you could say. There's I've already done an easier one before this. That's the easiest one you can do, and this is a little bit more difficult. And then there's the combination of these two will give you the most complex kind of projectile motion problems, in which you do you have two different delta y's, and you kind of have to take that into consideration. But we're not doing that in this problem. So again, just your delta dy is simply a 0. So when we sub in or whatever, I like to actually solve for my unknown first, just because I don't like to move around numbers. For me it's easier to move around variables. So we want to solve for essentially delta t squared, right? So what you can do is I can start off with this very assumption. I can start with this step. So delta dy, and the best thing to do, because we want to solve for delta t, and both these expressions here have delta t in them. So what I can do is I can kind of factor it out. So if I factor out delta t in the first expression, I'm just left with a v1y, and in the second expression I'm left with the half ay and another delta t. I'm still left with a delta t in the second expression because there's a delta t squared, right? So delta t times delta t gives me delta t squared. Now on this side of the equation, I can take delta dy, and I can kind of take this delta t to the other side, and so I have this expression, and on this side I'm just simply left with v1y plus half ay delta t. Now you're going to be like, oh, we still have two delta t's on each side, so what are we going to do? But now recall that this here equals 0, and 0 divided by, I don't care, like delta t does have a value, but 0 divided by anything is going to just give me a 0. So I'm essentially left with 0 equals v1y plus half ay delta t. So there you go. Now we've kind of we have just one delta t term, and we can essentially just solve for that. So when I take v1y to the other side, because I had a 0, so just go back here because I had a 0, and if I take v1y to the other side, I just get a negative v1y equals half ay delta t. So I've got that, and I can really easily just solve for delta t in one step. So delta t gives me, and I can take all of these things to the other side. So if it's a half, it's kind of like it's a half here, so it'll multiply on the other side. So I'd get negative 2 v1y, and because ay is multiplying, it's going to divide on the other side. So there we go. We have an algebraic expression to solve for delta t, and we have all the givens on the right hand side of the equation, so we can just sub that in. So delta t equals -2, and v1y, remember v1y was actually v1 times sine 55 because we broke it down into components, and v1 itself is 10.7. So essentially I have -2 times 10.7 times sine 55. So that's my v1 expression right here. And this whole thing divided by -9.8 meters per second squared. And here it is meters per second, so if you really want to write that. So after so you can see that clearly that the two negative signs cancel out. After you plug these into your calculator, you should get an answer that looks like this. So 1.7887 seconds. Now, as before, are we going to leave it like this? Nope, because we let's see, what did we start off with? We have 3 significant digits here. Generally for the angle, we don't, the angle is kind of like, I guess you could say, somewhat constant. So we don't look at the like an angle is always 2 significant digits, so we don't look at the significant digits there. I would stick with 3. So in this case, we would say that it's let's go with 1.80. 1.80 seconds. So that's the time of flight of your football, essentially. Now the question was, with 6 seconds to go in the 4th quarter, will Colston receive the pass before the clock runs out? Well, yes, because there's 6 seconds on the clock, but it just takes the football to travel that distance. The time of flight of the football is just 1.8 seconds. So and have your nice little statement over here, and you can write yes, Colston will receive the pass before the clock runs out. So that's your answer. So you've got part A, all figured out, and it was really easy. You can see, just as long as you got the gist of the, what part A was actually asking about. It was actually asking me about, okay, what is delta t? So we got that figured out. So let's move on to part B. And part B might be a little bit more confusing for some of you, but essentially it's your regular. So it's just your regular, distance problem. It's asking you for the range. So what distance does the football actually cover when it's thrown? So, and when we drew our diagram, we could see that Drew Brees throws it and it goes in. It does follow like a parabolic motion, but it actually does. There's a certain distance or displacement in the x direction that the football covers. So we although it asks will Colston receive the pass if he's standing 30 meters away from Brees, what we really want to find out is that, okay, how far does the football actually go? Then when we get that answer, we can actually figure out if it does go 30 meters, then we can say yes, okay, so Colston will receive the pass because the football covers 30 meters. But if it goes more or less, we can be like, no, he doesn't receive the pass because it's either beyond his reach, it falls before him, or it falls like behind him. So so we can in that case, how I would solve part B would be like such. Again, we have a bunch of given information. A new piece of given information for part B we have is delta t, because we figured that on part A. So we know that delta t is 1.7887 seconds. Note how I don't use my rounded off value. I did say, okay, it is 1.80 seconds, but because we're using our answer in another part of the problem, we want to get the most accurate answer we can. So we're not going to use a rounded off value. We're going to use the actual value we found. So that's a new piece of given information we have. What else do we know? Now we're considering only the x component, right? Because I'm asking what the range is in the x direction. So, you know, we're not concerned with anything in the y direction. So what else do we know? We know what v1x is, right? Because we can figure that out from our little trig kind of like triangle we had here. So because for the y direction we used the sine relationship, for the x direction you can see that this is the adjacent, this is the hypotenuse, and you know we have the angle here which is 55. And so basically I can use the cosine relationship. So that would be as such. So it basically is equal to v1 times cos 55. And essentially I'm just getting it like this because it's, so you have your cosine equals adjacent over hypotenuse. Your adjacent was your v1x. So you can say that your cos theta is your adjacent, which is v1x, over hypotenuse, which is your v1. But I'm actually looking for this, so I can just, you know, take this to the other side. So v1x would just simply be v1 cos theta, and you know theta is 55 degrees. So that's how I'm getting this, and that's exactly the same way how I got v1y, except it was just a sine relationship. So we have v1x. What other given information do we have? Well, you know, we can solve this by saying that v1, we know what v1 is, otherwise we can't solve for v1x. It's just 10.7 meters per second. And are we concerned with an acceleration here? Well, no, because you know, there's no acceleration in the x direction. That was, we only considered it in the first part of the problem because we were talking about the y direction. So in this case we can be like, okay, you know, it's uniform motion in the x direction, so there's no acceleration. So that leaves us with just delta dx. That's exactly what we're looking for. So you know, like super easy, we can easily solve this. The equation we use is your simple, you know, v1x equals delta dx. So your speed and velocity and time relationship over delta t. But what I'm looking for is actually delta dx. So I can write that delta dx is equal to v1x times delta t. And I know all my values, so you know I just stick them in there. So well, I should read it first, you know, just so you can follow the solution. So v1 cos 55 times 1.7887. So that's that. And so I can simplify this part here because I know what v1 is. So that would give me we're solving for delta d there. So delta dx, it would give you v1 was 10.7, right, times cos 55, and remember we're multiplying it by the time, so 1.77, not 1.77, sorry, 1.887. And again, you know, just simply plug this into your calculator and you should get a number like this, so 10.977 meters. So that's the range. So you know this equals range. And again, when you round it up to about 3 significant digits, I would just, you know, put this as 11.0 meters. Now again, what was the question asking us? The question was actually asking us, you know, will Colston receive the pass if he's standing 30 meters away? Well, unfortunately, Colston will not receive the pass if he's standing 30 meters away because the range the football covers is only 11 meters. So, you know, that can be, you can write your concluding statement, and very simply, no, Colston will not receive the pass if he is standing 30 meters away because the range is only 11.0 meters. So that's it. You know, that's essentially how I would do this problem, and it's super easy. Again, you know, not the most complex type, but not the most easiest either. So if you follow these steps, you will pretty much get the right answer every single time. And keep coming back to my channel.